During the first moon landing, Eagle's computer flashed alarms no astronaut recognized, but the machine was discarding low-priority work exactly as its designers intended. On July 20, 1969, Eagle was descending toward the moon when Neil Armstrong called out a message from the guidance computer, Program Alarm, 1202. The lunar module was about 33,000 feet above the surface and falling toward a landing from which there was no simple pause button. Armstrong and Buzz Aldrin did not recognize the code. Mission Control had seconds to decide whether it meant the computer had lost control or whether the descent could continue. 10 seconds after Armstrong reported the number, Houston answered that Eagle was go on the alarm. The computer had announced an overload during the most consequential approach ever attempted, and the people on Earth had chosen not to abort. The Apollo guidance computer was tiny by modern measures, but comparisons based only on memory or clock speed miss its purpose. It was a real-time control system designed to navigate, steer, and manage the spacecraft with predictable behavior. During powered descent it accepted measurements, estimated Eagle's state, commanded the descent engine, drove cockpit displays, and kept critical guidance programs running. The machine could not postpone that work while it processed a convenient backlog. Each calculation had a deadline tied to a moving vehicle. Its software therefore needed a way to decide which jobs mattered most when more work arrived than the processor could complete. The source of the extra work was the rendezvous radar system. That radar existed to help the lunar module find the command module in lunar orbit, especially after leaving the surface. During descent, switch positions and the electrical relationship between the radar and guidance computer produced repeated requests for radar-related processing. NASA's post-mission explanations describe extraneous data from the rendezvous radar consuming computer time. The radar was not helping Eagle land. It was creating interrupts and scheduling work while the computer was already solving the landing problem. The result was not corrupted navigation data so much as a queue that was filling faster than the executive could comfortably clear it. Alarm 1202 meant that the computer could not obtain a free core set for another scheduled job. A related 1201 alarm indicated another form of executive overflow. Those numbers were compact diagnostic codes, not plain language instructions. They told specialists what internal resource had run out, but the crew could not infer the consequence merely by seeing 4 digits. An overload can describe anything from a harmless dropped background task to the loss of a control loop. What mattered was not only why the alarm appeared, but what the Apollo software did next. That behavior had been designed and tested long before Eagle reached the moon. The guidance computer used a priority-driven executive. When overloaded, it could restart and restore the essential programs near the point where they had been interrupted. Steering the descent engine, maintaining guidance, and operating the display and keyboard remained important. Erroneously scheduled radar work did not receive the same protection. In a modern analogy offered by one of the software engineers, an ordinary reboot might close everything. Apollo's restart logic could bring back the work needed to continue while leaving unnecessary background activity behind. The alarms did not mean the computer had surrendered. They meant its safeguards were shedding work to preserve control. That distinction had to cross several people in seconds. Guidance Officer Steve Bales monitored the lunar module's navigation and computer state in mission control. Jack Garman, a specialist who had studied the guidance computer alarm codes, supported the decision. The team recognized that the computer was continuing to produce valid guidance and that the overload pattern was one the restart protection could handle. Their answer traveled through the flight control chain to capsule communicator Charlie Duke, who told the crew they were go. The famous call was therefore neither guesswork nor one heroic person's intuition. It was a prepared organization using telemetry, training, specialist knowledge, and a clear authority path under severe time pressure. The alarm returned. NASA's mission history records additional 1202 alarms and a 1201 as Eagle descended. Each recurrence forced the same practical question: was the computer recovering while retaining essential control? Mission Control continued to receive enough evidence to say yes. The spacecraft did not tumble, guidance did not disappear, and the descent program continued. A warning that repeats can tempt operators either to ignore it automatically or to overreact because it feels increasingly urgent. The controllers did neither. They interpreted each alarm in context, checked the system's behavior, and repeated the go recommendation while the conditions remained acceptable. The computer alarms were only one problem during the final approach. Eagle was heading toward a boulder-strewn area near a crater rather than the smooth patch Armstrong wanted. He took more direct control of the landing attitude and flew forward to find safer ground. Propellant call updates continued as the remaining margin narrowed. Communications were imperfect, partly because antenna geometry affected the high-rate link. These overlapping concerns explain why the overload mattered even though the computer handled it correctly. A recoverable alarm still consumed the attention of astronauts and controllers at the precise moment they needed to assess terrain, fuel, navigation, and the option to abort. Eagle landed safely in the Sea of Tranquility. After touchdown, investigators traced the overload in detail. Accounts differ in shorthand about exact switch terminology and electrical phasing, but the broad result is consistent across NASA's histories and the mission report. Rendezvous radar activity imposed unintended processing demand, causing 5 computer overload alarms during descent. The crew had followed procedures used in training. The simulated setup had not reproduced the full interaction in the same way. This was not simply an astronaut choosing an obviously wrong switch or a programmer forgetting to handle overload. It was an interface and test problem that appeared only when real subsystems operated together. The episode is often described as a computer failure, yet the computer's recovery was one of the mission's successes. The initiating condition was undesirable, the alarms were disruptive, and an abort could have followed if the team could not establish that guidance remained safe. But the priority executive and restart routines did what robust real-time software should do: preserve the highest value work when demand exceeds capacity. Graceful degradation is more useful than pretending overload can never happen. Apollo's designers accepted that finite hardware could face unexpected combinations and built a controlled way to lose less important work first. Testing was equally important. Engineers had exercised the restart capability before flight, giving controllers evidence that it could recover essential programs. Yet the end-to-end training environment did not fully expose the rendezvous radar interaction. Both truths belong in the lesson. Component resilience prevented failure, while incomplete integrated simulation allowed the overload condition to reach the mission. Modern safety-critical systems need both. They require deterministic priorities and restart behavior inside the computer, plus realistic tests that connect sensors, switches, timing, operators, procedures, and simulators as the deployed system will connect them. Apollo 11's 1202 alarm has endured because it reverses the usual story about old computers. The machine was not saved by someone quickly adding more processing power. No patch arrived during descent. The recovery came from decisions embedded before launch: rank work by importance, detect resource exhaustion, restart safely, preserve observable state, train specialists on obscure codes, and let those specialists advise a disciplined control team. The alarm was real, and so was the risk of an unnecessary abort. But the overload did not take control away from Eagle. In the moment the computer had too much to do, it demonstrated that its designers had already decided what it must never stop doing. The event also shows why observability must be designed for the people who make the recovery decision. A 4-digit code was efficient for a constrained display, but useful only because a support team could connect it to processor state and current guidance performance. A resilient controller should not merely restart, it should leave enough evidence for operators to know what was discarded, what resumed, and whether safety margins remain. Alarm catalogs, telemetry, rehearsed authority, and concise communication are part of the fault tolerance system. If the crew had received only an unexplained warning and mission control had lacked the underlying measurements, identical software behavior might still have produced an abort. Technical recovery and human confidence had to arrive together. That combination is why the right lesson is broader than the computer worked. The machine contained the overload, the telemetry exposed its condition, specialists interpreted it, and the organization delivered a decision before the descending spacecraft made the decision irrelevant.